Look up at the night sky, and what do you see? A scattering of stars, perhaps a planet or two, the faint glow of the Milky Way. But what if I told you that everything visible to the naked eye makes up less than 5% of the universe? The rest is hidden in plain sight, a cosmic game of hide and seek played on a scale so vast it defies imagination. Dark matter, mysterious signals from deep space, galaxies that shouldn't exist. These are just a few of the universe's carefully guarded secrets, puzzles so profound they've left even the brightest minds scratching their heads. And here's the thing, the more we learn, the more we realize how much we don't know. Think about that for a moment. We've sent probes to the edge of our solar system, built telescopes that peer back in time to the dawn of creation, and yet the cosmos still holds onto its mysteries with a stubborn grin. It's as if the universe is whispering riddles just beyond our reach, teasing us with clues that only lead to deeper questions. Why does dark energy seem to be tearing space apart? What are those strange, repeating radio bursts from distant galaxies? And how can entire galaxies rotate as if they're being tugged by invisible hands? These aren't just scientific curiosities, they're cosmic conundrums that challenge the very foundations of what we think is possible. That's where this journey begins. Over the next 40 cosmic riddles, we'll unravel the universe's greatest enigmas, the ones that keep astronomers awake at night and philosophers staring at the stars. Some of these mysteries might sound like science fiction, but they're very real, hidden in the data, etched into the fabric of space itself, waiting for someone to connect the dots. And the strangest part, the answers might be right in front of us, camouflaged by the ordinary, disguised as background noise. So buckle up. By the time we're done, you'll never look at the night sky the same way again, because once you see the universe's secrets, you can't unsee them. The question is, are you ready to play the universe's game? Consider this. Our galaxy alone contains hundreds of billions of stars, many with planets orbiting in the so-called Goldilocks zone where life could thrive. Multiply that by the 2 trillion galaxies we've observed, and the numbers become mind-bending. Statistically, the universe should be teeming with civilizations, so why does it feel like we're shouting into an empty room? This is the Fermi Paradox in action, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One unsettling theory is the Great Filter, an invisible wall that prevents life from advancing too far. Maybe simple life forms emerge often, but intelligence is a fluke. Or perhaps every advanced civilization hits a self-destruct button, whether through war, environmental collapse, or some unseen cosmic danger. If that's true, the filter could still lie ahead of us, lurking in humanity's future like a shadow we haven't noticed yet. Then there's the zoo hypothesis, the idea that extraterrestrials might be deliberately avoiding us, observing from a distance like scientists watching animals in a nature preserve. Or maybe we're searching the wrong way. Our radio telescopes listen for deliberate signals, but what if advanced civilizations communicate through neutrino beams or quantum entanglement, technologies we can't yet detect? The silence might also hide something stranger. Life could take forms we wouldn't recognize, not carbon-based creatures, but AI minds living in Dyson spheres, or beings made of plasma drifting between stars. The universe's rules might allow for civilizations so advanced, their presence blends into the background of space-time itself. Whatever the answer, the Fermi Paradox does one thing brilliantly: it humbles us. In a cosmos this vast, our solitude, or the illusion of it, forces us to confront how little we understand. Every quiet star could be hiding a secret every empty patch of space a riddle waiting to be solved. So while we keep listening, keep searching, remember, the absence of proof isn't proof of absence. The universe has a way of surprising us when we least expect it. Picture a spinning carousel, but one where the outer horses move just as fast as the inner ones, defying all logic. That's exactly how galaxies behave. Stars on the outer edges orbit at speeds that should send them flying into space, yet something unseen holds them in place. This cosmic tug of war points to an invisible player, dark matter. It doesn't emit light, absorb it, or reflect it, but its gravitational grip is undeniable. Without it, galaxies would unravel like yarn in zero gravity, their stars scattering into the void. So what is this ghostly substance? The leading theory suggests it's a sea of exotic particles, perhaps WIMP, or weakly interacting massive particles that barely interact with normal matter except through gravity. But after decades of hunting with ultra-sensitive detectors buried deep underground, we've come up empty-handed. Some scientists are now questioning if we've been chasing a phantom. Could dark matter instead be a sign that Einstein's theory of gravity needs revising? Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently at galactic scales, eliminating the need for invisible matter altogether. Yet even MUND can't explain all the cosmic fingerprints dark matter leaves behind, like the way it bends light around galaxy clusters in eerie cosmic mirages. The plot thickens when you realize dark matter isn't just passive scaffolding, it's an active architect. Computer simulations show that without its gravitational blueprint, the universe's web-like structure of galaxies and voids could never have formed. It's as if the cosmos relied on an invisible hand to sculpt itself into the universe we recognize today. And here's the twist: dark matter might not be one thing, but many. Some theories propose a shadowy ecosystem of particles, each with different properties, interacting in ways we can't yet fathom. Perhaps the most tantalizing clue lies in the Bullet Cluster, where two galaxies collided, leaving their dark matter trailing behind like smoke from a passing train. This cosmic accident revealed a surreal separation. Most ordinary matter, slowed by friction, lagged in the middle, while the unseen mass, revealed by its gravitational lensing effect, raced ahead. It's as close as we've come to seeing dark matter without actually seeing it at all. The deeper we dig, the stranger it gets. Some experiments have detected unexplained signals that could be dark matter particles decaying or interacting. Others suggest dark matter might occasionally smash into neutron stars, leaving behind telltale heat signatures. But until we catch it red-handed, this cosmic fugitive remains at large, weaving its way through our equations and our telescope's blind spots. One thing's certain: solving this riddle won't just fill a gap in our knowledge, it could rewrite the rules of the universe as we know them. If dark matter is the universe's invisible scaffolding, then dark energy is its most baffling magic trick, a force so strange it makes galaxies flee from each other faster than light itself. Picture a loaf of raisin bread baking in the oven where the raisins are galaxies. Normally, you'd expect the expansion to slow as gravity pulls everything together. But in our cosmic kitchen, the dough is stretching faster and faster, as if some unseen hand cranked up the heat. That's dark energy in action, not just expanding the universe, but accelerating its expansion against gravity's relentless tug. When astronomers first discovered this in the late 1990s, it shattered expectations. By measuring distant supernovae, they found the universe wasn't merely coasting. It was pressing the gas pedal harder with time. The implications were staggering. Either 70% of the universe's energy budget is tied to something we can't see or touch, or Einstein's theory of gravity, the cornerstone of modern physics, is incomplete. The leading theory pins dark energy on the cosmological constant, a term Einstein once called his greatest blunder. It suggests empty space isn't truly empty but seethes with latent energy, stretching spacetime itself. Yet the math is wildly off. Quantum physics predicts this energy should be a staggering 10 to the power of 120 times stronger than observed. That's like expecting a hurricane and feeling only a whisper of wind. Alternative ideas abound. Maybe dark energy isn't constant but evolves, a dynamic field nicknamed quintessence after the ancient fifth element. Or perhaps our three-dimensional universe is brushing against hidden extra dimensions, leaking gravity and warping expansion in ways we can't yet fathom. The wildest possibility, dark energy hints at multiple universes bubbling into existence in an endless multiverse, each with its own rules. Here's where it gets eerie. If acceleration continues, distant galaxies will eventually vanish beyond an invisible horizon, their light too stretched to ever reach us. Future civilizations might gaze at a sky nearly empty of galaxies, with no clues that a vast cosmos once existed beyond their own stellar island. Dark energy doesn't just hide secrets, it might erase them completely. Yet for all its mystery, dark energy leaves fingerprints. Giant galaxy surveys map its push on cosmic structures, while telescopes like Euclid and the Vera Rubin Observatory hunt for distortions in spacetime itself. The answer could lie in the subtle warping of light or the way galaxy clusters drift apart like leaves on a rushing river. One thing's clear, dark energy isn't just a puzzle. It's a countdown clock ticking toward a future we're only beginning to imagine. Somewhere beyond the Milky Way's shimmering veil, a cosmic siren calls, an unseen force so powerful it's dragging entire galaxies toward it at millions of miles per hour. Astronomers call it the Great Attractor, and it's one of the universe's most perplexing riddles. Imagine tossing a handful of leaves into a river, only to watch them all drift toward the same mysterious whirlpool. That's exactly what's happening to galaxies in our corner of the cosmos, including our own Milky Way, all pulled toward a point in space we can't even see. The challenge, this gravitational epicenter hides directly behind the plane of our galaxy, buried behind thick clouds of dust and stars that block our view like a cosmic curtain. For decades, it was like trying to study a lighthouse through a sandstorm. But thanks to infrared and radio telescopes piercing through the obscurity, we've begun mapping the unseen. What we've found is both dazzling and bizarre. The Great Attractor isn't just a single massive object, it's part of an even larger puzzle, a sprawling supercluster of galaxies nicknamed Laniakea, Hawaiian for immeasurable heavens. This cosmic metropolis spans 500 million light-years, with thousands of galaxies bound together in a delicate dance of gravity. Yet even Laniakea might not explain the full strength of the pull. Some researchers suspect something even grander lurks beyond it, perhaps an immense concentration of dark matter, or a chain of superclusters we've yet to map. Others wonder if the Great Attractor is just one piece of a larger flow, a cosmic river guiding galaxies toward an unfathomably massive structure billions of light-years away, like the Shapley supercluster. Here's where it gets stranger. The laws of gravity as we know them can't quite account for the sheer scale of this motion. Could there be exotic physics at play, or hidden dimensions warping the fabric of space in ways we don't yet understand? Or is the Great Attractor a fleeting illusion, a snapshot of a universe so dynamic that what we're seeing is just a momentary ripple in the grand scheme of things? Every new observation deepens the mystery. Galaxy motions reveal subtle inconsistencies, as if the universe is whispering hints just beyond our grasp. Future telescopes, like the Square Kilometre Array, aim to trace these flows with unprecedented precision, peeling back layers of this cosmic onion. One thing's certain, solving the riddle of the Great Attractor won't just reveal what's pulling us, it'll rewrite our understanding of how the universe structures itself on the grandest scales. And until then, we're all caught in its current, racing toward an answer hidden in the dark. One moment, the cosmos is silent. The next, a blast of radio waves brighter than a billion suns rips across the universe, then vanishes without a trace. These are fast radio bursts, or FRB, some of the most baffling signals ever detected. Lasting just milliseconds, they pack more energy than our sun emits in decades, arriving from galaxies so distant their light has traveled billions of years to reach us. And the strangest part, some burst once and disappear forever, while others repeat on cryptic schedules like cosmic alarm clocks set to no rhythm we can decipher. Take FRB 1214, nicknamed the Lorimer Burst after its discoverer. This single, brilliant flash in 2007 was so unexpected, some dismissed it as telescope glitch until more followed. Then there's FRB 1211, the first known repeater, flickering on and off like a malfunctioning beacon. Its signals aren't random, they arrive in windows of activity followed by eerie silence. What could possibly power such precise yet unpredictable fireworks? Theories abound, each more tantalizing than the last. Magnetars neutron stars with magnetic fields 1,000 trillion times stronger than Earth's top the list. When these cosmic powerhouses experience starquakes or magnetic eruptions, they might unleash FRBs like celestial lightning strikes, but not all bursts fit this mold. Some are too energetic, others too frequent. Then there's the Blitzar hypothesis. Imagine a supermassive neutron star spinning so fast it's on the verge of collapsing into a black hole. In its final moments, the dying star's magnetic field snaps like a rubber band, releasing a catastrophic burst of energy. But let's be honest, the elephant in the room is the possibility, however slim, that we're hearing alien engineering. Some FRBs pulse with mathematical regularity, sparking debates about artificial origins. Could they be interstellar lighthouses or the byproduct of light sail propulsion, where distant civilizations beam energy to spacecraft? Even skeptics admit the timing is uncanny. The signals often arrive in frequencies that slice neatly through interstellar gas, as if optimized for long-distance travel. Here's where it gets weirder. In 2020, astronomers caught an FRB originating inside our own galaxy and attached it to a known magnetar, case closed. Not quite. This burst was weaker than its extragalactic cousins, leaving open the chilling possibility that multiple phenomena create similar signals. Worse, some FRBs exhibit scattering, where their waves stretch out as if passing through turbulent plasma. One detected in 2022 had a fingerprint unlike any other, hinting at environments so extreme they defy current physics. The universe, it seems, is toying with us. Every time we think we've pinned down FRBs, a new burst breaks the mold. New telescopes like CHIME and the upcoming square-kilometer array are scanning skies around the clock, turning up dozens more, each a fresh clue in this cosmic whodunit. One thing's certain, solving this riddle won't just reveal what's causing these bursts. It might force us to rethink how energy, matter, and even intelligence manifest across the cosmos. Until then, the stars keep whispering in code, and we're just beginning to learn the alphabet. August 15, 1977. A quiet night at Ohio State University's Big Ear radio telescope. Then, out of nowhere, a signal so powerful it blasted through the static, a narrowband radio scream 30 times louder than the cosmic background noise. For 72 seconds, it held steady, peaking at the exact frequency hydrogen absorbs and emits energy, a natural choice for interstellar communication. Then, just as suddenly, it vanished. Astronomer Jerry Amon circled the data printout in red pen, scribbling one word beside it: "Wow." And with that, the most tantalizing and frustrating mystery in SETI history was born. What made the WOW signal extraordinary wasn't just its strength, but its behavior. Natural cosmic radio sources, pulsars, quasars, don't turn on and off like a switch. They flicker, drift, or persist. This was surgically precise, appearing only in one of the telescope's two beams, as if the source moved out of range. Yet despite decades of follow-up scans, including Amon's own relentless searches, the signal never repeated, not once. So what could explain it? The obvious suspect was a passing comet, except none were in the area that night. Solar flares too narrow in frequency, satellite reflection, no known human transmissions matched its profile. Even if it was artificial, the implications are staggering. The signal came from the direction of Sagittarius, near the center of our galaxy where stars are packed like sand. For a transmission that strong to reach us, it would have required a focused beam with the power of a small star, aimed deliberately at Earth. Here's where the debate ignites. Critics argue it could have been an undiscovered natural phenomenon, maybe a rogue hydrogen cloud interacting with a black hole in some exotic way. Others, like astronomer Antonio Paris, later proposed two comets with hydrogen-rich tails might have been the culprits, though their trajectories didn't quite line up with the signal's origin. Meanwhile, die-hard optimists point out that if aliens were signaling, they wouldn't necessarily repeat it. Imagine a lighthouse sweeping its beam across the ocean. By the time you see it, the light has already moved on. The WOW signal's legacy isn't just about what we heard, it's about what we didn't. In the years since, thousands of hours of SETI observations have turned up nothing remotely similar. It's as if the universe played a prank, leaving us with a single, flawless fingerprint and no suspect. Newer telescopes like the Allen Array now scan millions of frequencies simultaneously, but silence persists. Maybe the answer lies in next-gen tools like the upcoming Square Kilometre Array, capable of detecting fainter, faster signals. Or perhaps the real lesson is humility. In a cosmos this vast, some mysteries refuse to surrender their secrets easily. One thing's certain, that 72-second burst rewrote the rules. It taught us to listen differently, to expect the unexpected. Whether it was aliens, a quirk of physics, or something beyond our current understanding, the WOW signal remains a masterclass in cosmic curiosity. And somewhere out there, in the black velvet of space, the truth still drifts, waiting for the next eager ear to hear it. In the constellation Cygnus, a star named KIC 8462852, better known as Tabby's star, has been playing a cosmic game of peekaboo with astronomers. Unlike most stars, which dim in predictable rhythms from orbiting planets, this one flickers erratically, sometimes plunging in brightness by a staggering 22% before bouncing back. Imagine a light bulb that randomly fades to a faint glow, then flares to full strength with no discernible pattern. That's the enigma of Tabby's star, a puzzle so compelling it sparked headlines about alien megastructures and cosmic engineering on a scale beyond human comprehension. The story begins with NASA's Kepler Space Telescope, which hunts for exoplanets by catching the subtle dips in starlight as planets pass in front of their suns. But Tabby's star didn't behave like anything Kepler had seen before. Instead of tidy, periodic dimming, its light curves were chaotic, steep, asymmetrical drops lasting days or weeks, followed by long stretches of normalcy. The most dramatic event, a series of dips in 2017 where the star's light plummeted in a way no natural phenomenon could easily explain. Cue the theories. The most tantalizing and controversial suggested a Dyson swarm, a hypothetical cloud of energy collecting structures built by an advanced civilization to harness their star's power. Picture millions of giant solar panels orbiting in formation, occasionally blotting out the star's light as they pass. It's a sci-fi dream, but one rooted in real physics. After all, if a civilization wanted to maximize energy, surrounding their star would be the ultimate power move. But before we jump to aliens, let's talk dust. The leading explanation now points to vast, uneven clouds of cosmic debris, perhaps from shattered planets or swarms of comets, drifting in front of the star. Observations show the dimming is wavelength dependent, meaning shorter wavelengths of light are blocked more than longer ones, a classic fingerprint of dust. Yet even this theory has holes. The dust would need to be incredibly fine and clumpy to create such irregular patterns, and no known natural process produces dust clouds this dynamic. Then there's the star itself. Tabby's star is an F-type main sequence star, slightly hotter and larger than our Sun, but otherwise unremarkable, except for one quirk. Historical data from old photographic plates suggests it may have dimmed by as much as 14% over the past century, a change unheard of for stars like it. Could it be undergoing some rare phase of stellar adolescence, or is something else obscuring our view? The truth is, Tabby's star defies easy categorization. It's not just one mystery, but layers of them, each observation peeling back a new question. Future telescopes, like the James Webb Space Telescope, might analyze the dust's composition or spot hidden companion stars. Until then, this celestial oddity stands as a reminder. Sometimes the most profound discoveries aren't found in the exotic corners of the universe, but in the subtle anomalies of the familiar. And whether the answer is dust, aliens, or something stranger still, Tabby's star has already taught us one vital lesson: the cosmos always keeps a few surprises up its sleeve. In the vast emptiness beyond Pluto, two robotic pioneers, Pioneer 10 and Pioneer 11, were supposed to coast silently into interstellar space, their trajectories governed by the precise laws of gravity. But something odd happened. As they ventured farther from the Sun, both spacecraft began slowing down ever so slightly, as if an invisible hand had gently tapped the brakes. This unexpected deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, a tiny deviation that sent shockwaves through the world of physics. At first, scientists assumed it was a simple engineering glitch. Maybe heat, radiating unevenly from the probe's power systems, was nudging them off course. After all, even the slightest thermal emission can act like a miniature thruster in the vacuum of space. Teams pored over decades of telemetry data, reconstructing every possible source of onboard heat, from electrical systems to the slow decay of radioactive power sources. Yet when they crunched the numbers, thermal radiation could only account for part of the anomaly. The rest remained stubbornly unexplained. This raised a far more tantalizing possibility. What if the anomaly wasn't a technical hiccup, but a sign of new physics? Some theorists proposed modifications to Einstein's theory of gravity, suggesting that on cosmic scales, gravity might behave differently than we thought. Others floated the idea of unseen dark matter subtly tugging at the probes, or even exotic forces linked to the fabric of spacetime itself, the most radical hypothesis. That we were seeing hints of higher dimensions, extra layers of reality, warping gravity in ways our current equations can't describe. Then came the twist. In 2012, after years of painstaking analysis, a team announced they'd cracked the case. By modeling the spacecraft's heat emissions in unprecedented detail, they concluded the anomaly was indeed thermal, just far more complex than anyone imagined. The probe's dish antennas, they argued, had been reflecting heat asymmetrically, creating a tiny but measurable push. Case closed, not quite. Skeptics pointed out discrepancies in the model, and even if heat explained most of the effect, some residual anomaly lingered, like a ghost in the data. The Pioneer Anomaly's legacy isn't just about solved or unsolved mysteries. It's a masterclass in scientific humility. These probes, launched in the 1970s with technology less powerful than a modern calculator, exposed gaps in our understanding that still ripple through physics today. Future missions, like the upcoming interstellar probes designed to leave the solar system faster and with better instrumentation, could finally put the debate to rest. Until then, the Pioneer's faint signal serves as a reminder. Sometimes, the universe's quietest whispers hold the loudest questions. We think of the universe as a vast, directionless expanse, no up, no down, no cosmic north or south. The laws of physics should hold true no matter which way you look, a principle called isotropy. But what if that's not entirely true? Hidden in the afterglow of the Big Bang itself, astronomers have stumbled upon a pattern so bizarre it's been dubbed the axis of evil. The cosmic microwave background, or CMB, is the oldest light we can see, a snapshot of the universe just 380,000 years after its birth. It should be a random, speckled canvas like static on an old TV, yet when scientists mapped its temperature fluctuations, they found something unsettling. The hot and cold spots aren't entirely random. Instead, they seem subtly aligned along a particular axis, as if the universe itself has a faintly marked "this way up" sign. This discovery sent shockwaves through cosmology. The standard model of the Big Bang predicts uniformity, no preferred direction, no hidden grid lines. The odds of this alignment happening by chance, less than 1 in 10,000. Some researchers dismissed it as a statistical hiccup, a cosmic mirage created by our limited perspective. But as more precise measurements came in, from WMAP to Planck, the pattern stubbornly persisted. So what could explain it? One radical idea suggests the axis of evil might be a bruise from a collision with another universe during inflation, a multiverse fingerprint pressed into our cosmic infancy. Others propose it's evidence of primordial magnetic fields or exotic physics warping spacetime before the first stars flickered to life, the wildest theory. That we're seeing the imprint of a universe that existed before the Big Bang, a ghostly echo of a previous cycle of creation. Even stranger, this axis eerily aligns with our solar system's plane, as if the universe is whispering a secret just for us. That's almost certainly a coincidence, but it's the kind of coincidence that keeps scientists awake at night. Could there be some observational bias, some overlooked quirk in how we measure the CMB? Or does the axis of evil hint that our universe isn't the featureless void we imagined, but a structure with hidden symmetries, like a hall of mirrors we've only just noticed? The implications are staggering. If the universe has a preferred direction, it could rewrite our understanding of inflation, dark energy, even the arrow of time itself. Future telescopes like the Simons Observatory aim to probe the CMB with unprecedented precision, hunting for clues in the polarization of ancient light. Until then, the axis of evil remains one of cosmology's most tantalizing loose threads, a reminder that sometimes the universe's boldest secrets are written in the faintest ink. Imagine two coins flipped simultaneously on opposite sides of the universe, yet somehow they always land matching heads or tails, instantly mirroring each other no matter how far apart they are. This isn't science fiction, it's quantum entanglement, one of the most mind-bending phenomena in physics. Einstein famously dismissed it as spooky action at a distance, unable to reconcile it with his view of a predictable classical universe. Yet decades of experiments have proven entanglement is real. leaving us with a cosmic riddle that challenges everything we thought we knew about space, time, and the very nature of reality. At its core, entanglement occurs when particles like electrons or photons become inextricably linked, sharing a single quantum state. Measure 1, and its partner instantly assumes a corresponding property, even if separated by galaxies. The catch: this connection seems to happen faster than light, violating Einstein's cosmic speed limit. In theory, if you could use entangled particles to send Morse code, you'd have instant communication across the universe. But here's the twist: while the correlation is instantaneous, we can't actually control the outcome of measurements, making it useless for sending deliberate messages. It's like having a pair of magic dice that always match, but you can't choose which number they land on. The implications ripple far beyond communication. Entanglement hints that the universe might not be made of distinct, isolated objects, but a vast web of interconnected relationships. Some interpretations of quantum mechanics suggest particles aren't truly separate until observed, as if reality itself is a cosmic game of 20 questions, where the answers only solidify when we ask. This non-locality has philosophers debating whether the universe is fundamentally holistic, with every part subtly influencing the whole. Experiments keep pushing the boundaries. Scientists have entangled particles over distances exceeding 1,200 kilometers, even beaming entangled photons between satellites and Earth. In 2020, researchers demonstrated quantum entanglement between macroscopic objects, tiny drums visible to the naked eye, proving this weirdness isn't confined to the subatomic world. Yet the deeper we dig, the stranger it gets. Recent experiments suggest entanglement might even defy our arrow of time, with measurements appearing to influence events in the past, a phenomenon called retrocausality. Could entanglement unlock technologies we've barely dreamed of? Quantum computers already harness it to perform calculations impossible for classical machines. Some theorists speculate advanced civilizations might use entangled networks as a universal internet, or even manipulate it to engineer spacetime itself. But perhaps the most profound lesson is humility. Entanglement forces us to confront that the universe doesn't owe us intuitive explanations. It operates by rules that might forever hover just beyond the edge of our understanding. And in that uncertainty lies the thrill of the hunt, the reason we keep probing the quantum shadows, searching for the next clue in nature's grandest mystery. Black holes are cosmic shredders, tearing apart stars and swallowing light itself. But their greatest mystery isn't what they destroy, but what they might preserve. According to quantum mechanics, information, the fundamental blueprint of every particle state, can never be truly erased. Yet black holes, with their monstrous gravity, appear to violate this sacred rule. This is the information paradox, a clash between two pillars of physics that's kept scientists arguing for decades. The problem starts with Hawking radiation. In the 1970s, Stephen Hawking showed that black holes aren't completely black. Quantum fluctuations near the event horizon cause them to slowly leak energy, evaporating over eons. Here's the catch: this radiation seems random, carrying no trace of the matter that fell in. If a black hole vanishes, taking its secrets with it, what happens to the information encoded in all those swallowed stars? Quantum theory insists it must survive somehow, but general relativity paints a grim picture. Anything crossing the event horizon is lost forever, crushed into a singularity where space and time break down. One daring solution: the information isn't gone, it's scrambled. Think of a library set on fire. The books burn, but if you could somehow collect every charred fragment, every wisp of smoke, you might reconstruct their content. Some physicists argue black holes do something similar, encoding swallowed data in the chaotic swirl of Hawking radiation. It's not neatly preserved, but hidden in quantum correlations so complex they'd make a supercomputer weep. Then there's the holographic principle, a radical idea suggesting all the information inside a black hole is actually smeared across its surface, like a cosmic DVD encoding three-dimensional reality in 2 dimensions. If true, the event horizon isn't just a point of no return, it's a frenzied hard drive storing data in Planck-sized pixels. This would mean our universe itself might be a hologram, with black holes as the ultimate Rosetta Stones. But not everyone's convinced. Critics point to the firewall paradox. If information escapes via Hawking radiation, the event horizon should be a searing wall of energy, incinerating anything approaching it. A direct contradiction of relativity's prediction that falling into a black hole would feel uneventful until it was too late. Others propose fuzzballs, theoretical objects where black holes aren't empty pits but tangled knots of strings from string theory, bristling with preserved data. The stakes couldn't be higher. Solving this paradox might unlock a unified theory of quantum gravity, bridging the gap between the infinitely large and the vanishingly small. Future experiments, like measuring gravitational waves from colliding black holes, could offer clues. Until then, the paradox stands as a testament to the universe's stubborn refusal to fit neatly into our equations, and the thrilling possibility that black holes aren't cosmic dead ends but puzzles waiting to be decoded. The moon hangs in our sky like a silent sentinel, pockmarked and pale, a world we've walked on, yet one that still guards ancient secrets among its most puzzling. The magnetic ghost hiding in its rocks, samples brought back by Apollo astronauts contain traces of magnetization, as if the moon once crackled with a magnetic field as strong as Earth's. But today, our lunar neighbor is magnetically barren. What could have powered such an invisible shield, and why did it vanish? The leading suspect is a lunar dynamo, a churning ocean of molten metal in the moon's core, spinning and swirling like Earth's own magnetic engine. But here's the catch: dynamos need fuel. On Earth, our magnetic field is stoked by the slow crystallization of the inner core, releasing heat that keeps the outer core's metals swirling. The moon, though, is far smaller. Its core should have cooled rapidly, snuffing out any dynamo within 1 billion years of its formation. Yet the rocks tell a different story. Some lunar samples suggest the field persisted for over 1 billion years longer than physics predicts, like a candle burning in a vacuum. This timeline mismatch has scientists scrambling for explanations. Maybe colossal asteroid impacts rocked the moon's interior, stirring its core like a spoon in molten soup. Simulations show a massive strike could have jolted the dynamo back to life, at least temporarily. Others propose the moon's core was laced with lighter elements like sulfur, lowering its melting point and prolonging the chaos needed for magnetism. Then there's the wild card, gravitational kneading from Earth. In its youth, the moon orbited much closer, and our planet's tidal pulls might have stretched and squeezed its core, generating friction heat like warming a paperclip by bending it. The mystery deepens when you realize a lunar magnetic field shouldn't have existed at all. Planetary dynamos usually require rapid rotation, think Earth spinning once a day. The moon, tidally locked to us, turns glacially slow. How could such a sluggish world whip up a magnetic storm? Some theories suggest its early rotation was far quicker, or that its core operated on entirely different principles, perhaps with exotic materials we've yet to identify. The implications stretch beyond lunar history. If small, rocky worlds can harbor magnetic fields against the odds, exomoons around distant gas giants might too, raising tantalizing possibilities for habitable environments beyond planets. Meanwhile, NASA upcoming Artemis missions aim to drill deeper, hunting for rocks that capture the moment the moon's magnetic heartbeat faded. Each sample is a time capsule, holding clues to a time when the moon wasn't the quiet globe we know, but a dynamic world with its own invisible armor. Perhaps the most humbling lesson is this: even the seemingly familiar can hide radical pasts. The moon's magnetic whispers remind us that cosmic mysteries aren't always light years away. Sometimes they're right overhead, written in stone we've held in our hands but have yet to fully decipher. On October 19, 2017, astronomers spotted something extraordinary streaking through our solar system, a visitor from the stars, named Oumuamua, Hawaiian for scout. This cosmic interloper wasn't just the first known object from another star system, it was a shape-shifting enigma that defied every expectation. At first glance, it appeared to be a simple asteroid tumbling silently through the void, but as telescopes tracked its path, something didn't add up. Oumuamua wasn't just coasting, it was accelerating, as if propelled by an unseen force. The first shock was its shape. Most asteroids and comets are roughly spherical or lumpy, but Oumuamua was long and thin, stretching perhaps 800 meters while being only 80 wide, like a cosmic cigar tumbling end over end. Then came the real puzzle: its speed. As it raced away from the sun, Oumuamua sped up slightly, a behavior typical of comets venting gas as they warm. Yet no tail or coma, the fuzzy halo of a comet was visible. It was as if Oumuamua was playing a celestial game of hide and seek, leaving behind clues but no answers. Scientists scrambled for explanations. Maybe it was a rare, dark comet, venting invisible hydrogen gas from its icy interior. Or perhaps solar radiation pressure was pushing on an ultra-thin, lightweight structure, a natural solar sail. But these theories required Oumuamua to have properties never seen before in a natural object. Enter the most controversial idea: could it be artificial? Harvard astronomer Avi Loeb famously suggested Oumuamua might be a relic of alien technology, perhaps a discarded light sail or probe from a distant civilization. The media erupted, but most researchers remained skeptical. After all, extraordinary claims require extraordinary evidence, and Oumuamua was already racing out of sight. The deeper mystery lies in what we didn't see. By the time Oumuamua was detected, it was already leaving our solar system, giving astronomers just weeks to study it. Was it truly a lone wanderer or the first of many? Subsequent searches revealed no clear interstellar siblings, though projects like the Vera Rubin Observatory aim to catch the next visitor earlier. Some estimates suggest there could be thousands of such objects passing through our solar system unseen at any given moment, each a potential messenger from another star. Oumuamua's legacy isn't just about one odd object, it's a wake-up call. For centuries, we've assumed interstellar space was empty, punctuated only by the rare star. Now we know it's teeming with unseen travelers, each carrying secrets from their birthplaces. Whether Oumuamua was a peculiar comet, a fragment of a shattered planet, or something even stranger, its fleeting visit taught us one thing: the universe is far weirder and far more crowded than we ever imagined. And the next scout could be hurtling toward us right now, carrying answers or deeper riddles from the dark. Take everything you can see, every star, planet, and galaxy, and pile it all together. Now double it. That's how much normal matter the universe should contain, according to our best calculations. But here's the cosmic kicker: half of it is missing. Not dark matter, not exotic particles, just regular protons and neutrons, the building blocks of everything tangible. This is the missing Baryon problem, and it's like balancing a checkbook where trillions of dollars have mysteriously vanished without a trace. Where could these baryons be hiding? Supercomputer simulations paint a universe woven with a vast cosmic web, threads of hot, diffuse gas stretching between galaxies like invisible spider silk. These filaments, theorists argue, might contain the missing matter, so thinly spread and scorching hot that they're nearly impossible to spot. Imagine trying to see steam rising from a cup of coffee in a foggy room. That's the challenge astronomers face when hunting these elusive strands. Some clues have surfaced in the shadows. The Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background, hints at electrons in these filaments scattering ancient light. Then there's the absorption of X-rays from distant quasars, which occasionally reveal the fingerprints of warm gas clouds along their paths. But these detections are whispers, not shouts, like catching glimpses of a ghost in a crowded room. The plot thickens when you realize this missing matter isn't just hiding, it's shape-shifting. Some baryons might exist in a state called WIM, the warm-hot intergalactic medium, a plasma so hot it glows in X-rays but too faint for current telescopes to map clearly. Others could be trapped in sprawling halos around galaxies, or even flung into intergalactic space by violent supernova explosions. What's at stake? If we can't account for half the universe's ordinary matter, it's like trying to understand a novel by reading only every other page. Future observatories, like the European Space Agency's Athena X-ray telescope, aim to scan the skies for these hidden reservoirs. Until then, the missing baryons remain a humbling reminder. Even the familiar parts of the cosmos can defy our grasp, hiding in plain sight while we scramble to rewrite the inventory of existence. Most of space is crowded with galaxies' bright islands in a vast cosmic ocean. But in the constellation Boötes, there's a hole in the universe so enormous it defies comprehension. The Boötes Void, nicknamed the Great Nothing, stretches an astonishing 330 million light-years across, yet contains only a handful of galaxies. To put that in perspective, if our Milky Way were placed inside it, we wouldn't have discovered another galaxy until the 1960s. This isn't just an empty patch, it's a cosmic desert so barren that light takes hundreds of millions of years to cross it, with almost nothing to illuminate along the way. So how does a void this vast even exist? The standard model of cosmology predicts some empty regions, formed as gravity pulls matter into web-like filaments, leaving gaps between them. But the Boötes Void is 60 times emptier than it should be, like finding a soccer field where 99% of the grass simply didn't grow. One theory suggests it's the scar of an ancient collision between our universe and another bubble universe during cosmic inflation, a multiverse bruise frozen in space-time. Others propose it's the aftermath of a feeding frenzy, where a hyper-advanced civilization stripped the region clean of stars, though there's zero evidence for such speculation. The void's few galaxies only deepen the puzzle. Those that remain are oddly clustered near the center, as if huddling for survival. Some show signs of recent star formation, suggesting they're not primordial relics but latecomers, perhaps ejected from the void's edges by gravitational slingshots. Then there's the dark flow, a controversial observation that certain galaxy clusters seem to drift toward the void, as if tugged by something beyond our observable universe. Could the Boötes Void be a gravitational sinkhole, draining matter from its surroundings? Perhaps the most unsettling possibility is that the void isn't empty at all, but filled with something invisible. Dark energy, which accelerates the universe's expansion, might operate differently here, pushing galaxies apart more aggressively. Or maybe the void contains vast clouds of cold, dark matter, so diffuse they don't clump into galaxies. Future telescopes like the Nancy Grace Roman Space Telescope could map the void's structure in unprecedented detail, searching for whispers of hidden mass or peculiar motions. For now, the Boötes Void stands as a cosmic paradox, a reminder that even in a universe overflowing with matter, true nothingness can exist on a scale that humbles the imagination. It challenges our theories, dares us to rethink how structure forms, and whispers a tantalizing question. Are we staring into a flaw in the cosmic fabric, or a window into realities beyond our own? The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of its infancy. But in the constellation Eridanus, there's a blemish on that picture, a cold spot so vast and unexpected it's made astronomers question their most basic assumptions. Stretching a mind bending 1.8 billion light-years across, the Eriedana Supervoid isn't just empty, it's colder than its surroundings, as if someone carved a cosmic freezer into the fabric of space itself. Here's why that's so strange. The CMB's temperature variations are usually tiny, fractions of a degree, reflecting the gentle density fluctuations of the early universe. But this spot is 70 microkelvin cooler than average, a blip that should be vanishingly rare in our standard cosmological models. Some calculations suggest the odds of such a large, cold region forming naturally are less than 1 in 50,000. It's like finding a single snowflake in a desert, perfectly preserved against all logic. So what could explain this cosmic anomaly? The leading theory points to the supervoid itself, a region with far fewer galaxies than average. As light travels through such voids, it loses energy climbing out of their gravitational wells, a process called the integrated Sachs-Wolf effect. But there's a problem. The Eriedana Supervoid, while enormous, isn't quite empty enough to account for the temperature drop. It's as if the cold spot is larger than the void we can see, hinting at unseen structures lurking beyond our maps. Then there's the exotic physics angle. Could this be evidence of a collision with another universe during inflation, leaving behind a bruise in space-time? Some theories propose defects in the quantum field that birthed our cosmos. Cosmic strings or textures might have created this oddity. Others suggest it's a window into higher dimensions where gravity leaks between branes in ways we can't yet model. The most unsettling possibility that the cold spot isn't a flaw in our models, but a flaw in reality itself. Alternative theories of gravity, like modified general relativity, struggle to explain it. Even dark energy, the usual suspect for cosmic oddities, doesn't quite fit. Future telescopes like the Simons Observatory aim to study the spot's polarization patterns, hunting for clues in the way ancient light twists as it passes through. Until then, the Eriedana Supervoid remains a cosmic Rorschach test. What you see in it might say more about your theories than about the universe itself. One thing's certain, anomalies like this don't break science, they make it. Every unexplained cold spot, every stubborn deviation, is a chance to peel back another layer of cosmic mystery. And in the vast quiet of the Eriedana Supervoid, the universe might be whispering its next great secret. Beyond Pluto's icy realm, the solar system doesn't just fade quietly into darkness, it slams into a wall. Astronomers call it the Kuiper Cliff, a mysterious boundary where the Kuiper Belt's population of icy objects suddenly plummets, as if someone drew a cosmic "do not cross" line in the void. This isn't just a gradual thinning out, it's an abrupt cutoff, like a bustling city skyline giving way to empty desert. And the strangest part, according to our best models, the Kuiper Belt should stretch much farther, its icy debris fading slowly into the Oort cloud. So what or who cleared the neighborhood? One spine-tingling possibility is Planet 9, a hypothetical world up to 10 times Earth's mass lurking in the outer darkness. Its gravitational pull could theoretically shepherd Kuiper Belt objects into odd orbits while sweeping others away, creating this sharp edge. Computer simulations show such a planet might explain other oddities too, like the way some distant objects cluster at tilted angles, as if nudged by an unseen hand. The catch, despite years of searching, no one's spotted it yet. Could it be hiding in a distant, elliptical orbit, so far out that a single trip around the Sun takes 20,000 years? Or is it a cosmic phantom, a glitch in our observations? But not all scientists are convinced. Alternative theories suggest the cliff might be a relic of the solar system's violent youth. Perhaps a rogue star passed too close billions of years ago, stripping away the outer Kuiper belt like a thief in the night. Others propose that early gravitational tugs from Jupiter or Neptune sculpted the belt's edge, flinging smaller objects inward while ejecting others into interstellar space. There's even a wild-card idea. What if the Kuiper Cliff marks the ancient feeding zone of a long-vanished sibling star, born alongside the Sun in a dense stellar nursery? The plot thickens when you realize the cliff isn't just empty, it's too empty. Surveys like the Outer Solar System Origins Project have found fewer objects beyond 50 astronomical units than statistics predict, as if something scrubbed the region clean. Future telescopes like the Vera Rubin Observatory could finally settle the debate by mapping faint, distant objects with unprecedented precision. Every new discovery, or lack thereof, brings us closer to answering whether the Kuiper Cliff is a signpost pointing to Planet 9, a fossil of cosmic history, or something even stranger. One thing's certain, this invisible boundary is more than just a curiosity. It's a tantalizing clue that our solar system's story isn't fully written, and that the most dramatic chapters might still be hiding in the dark just beyond the edge of our sight. The Milky Way isn't just a swirling disk of stars. It's wrapped in an invisible force field, a cosmic checkpoint that even our hardiest spacecraft struggle to cross. Scientists call it the Galactic Barrier, and when the Voyager probes approached it, they didn't just hit a wall. They stumbled into a particle storm. Cosmic rays, those high-energy bullets from deep space, suddenly spiked, while others mysteriously dropped off, as if someone had flipped a celestial switch. This wasn't just a boundary, it was a filter, a sieve in the fabric of our galaxy. So what's creating this barrier? The leading theory points to magnetic fields. Our galaxy is threaded with them, woven like invisible spider silk, and at the edges, these fields might tangle into a dense web, deflecting or trapping particles like a cosmic colander. But here's the twist, the barrier's effects are stronger than standard models predict. If it's just magnetism, why does it behave like a bouncer, picking and choosing which particles get through? Some researchers speculate there's more at play, perhaps a buildup of dark matter or exotic particles, creating a shield we can't yet detect. Then there's the timing. Voyager 1 crossed the barrier in 2012, followed by Voyager 2 in 2018, but their data didn't match perfectly. One detected a sharp drop in certain cosmic rays, the other saw fluctuations that came in waves. This inconsistency hints that the barrier isn't uniform, it's patchy, dynamic, maybe even alive in ways we don't understand. Could it be shaped by galactic winds, streams of charged particles blowing from the center of the Milky Way? Or is it a standing wave, a ripple frozen in space-time from some ancient collision? The most tantalizing possibility, the barrier isn't natural at all. While most scientists dismiss wilder theories, a few have wondered if advanced civilizations might manipulate galactic magnetic fields as a form of energy harvesting, or even as a way to quarantine regions of space. It's a long shot, but the universe has surprised us before. What's clear is this: the galactic barrier isn't just a line on a map. It's a reminder that even in our own cosmic backyard, there are frontiers we've barely begun to explore. And as Voyager's faint signals trickle back from the void, they carry a humbling message. The galaxy is stranger and more structured than we ever imagined. The next puzzle, figuring out who or what built the fence. The universe is expanding, that much we know, but ask how fast, and suddenly cosmologists start arguing like detectives with conflicting evidence. This is the Hubble Tension, a rift in astronomy so deep it threatens to crack the foundation of modern cosmology. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, measurements of nearby stars and supernova peg it closer to 73. A tiny difference, not when your margin of error is razor thin. This isn't just a rounding error, it's a cosmic discrepancy that suggests something fundamental in our understanding is broken. So where's the glitch? One camp argues dark energy might not be constant after all, but growing stronger over time, like a hidden hand cranking up the universe's accelerator. Others suspect exotic particles, perhaps a new type of neutrino or an undiscovered force skewing the early universe's energy balance, the wildest possibility. We're seeing fingerprints of a second Big Bang, a dark explosion that altered the cosmos in ways we're only beginning to grasp. The stakes couldn't be higher. If the tension persists, it could mean rewriting Einstein's equations or even redefining what we call empty space. Future telescopes, like the Nancy Grace Roman Space Telescope, aim to measure the expansion with unprecedented precision, hunting for clues in the warped light of distant galaxies. Until then, the Hubble Tension stands as a reminder. Even the most basic facts about our universe might still be up for debate. And in that uncertainty lies the thrill of discovery, the chance to peel back another layer of cosmic mystery. Out in the frozen wasteland beyond Neptune, something is playing puppeteer with the orbits of distant icy worlds. These far-flung objects don't drift randomly. They cluster in paths tilted at bizarre angles, as if an unseen hand is herding them. This cosmic choreography has astronomers convinced there might be a hidden giant lurking in the solar system's shadows, Planet 9, a world up to 10 times the mass of Earth, silently shaping the chaos from the darkness. The clues are written in the strange behavior of objects like Sedna, a dwarf planet with an orbit so stretched it takes 11,000 years to circle the Sun. Then there's the peculiar alignment of extreme trans-Neptunian objects, their elliptical paths all pointing in roughly the same direction, a pattern so unlikely to occur by chance that the odds are less than 1 in 15,000. It's as if a massive gravitational shepherd is keeping them in line. Computer simulations show a distant planet could explain these oddities, its gravity gently tugging these icy bodies into their peculiar dance. Yet after years of searching, Planet 9 remains stubbornly invisible. Why hasn't anyone spotted it? For starters, its hypothesized orbit is colossal, stretching so far from the Sun that a single year there could last up to 20,000 Earth years. At that distance, sunlight would be feeble, leaving any potential world cloaked in near-total darkness. Even our most powerful telescopes would struggle to catch a glimpse of something so faint and slow-moving. Skeptics argue the evidence might be a cosmic mirage. Could these orbital oddities be the result of a passing star's gravitational nudge, frozen in time from the solar system's infancy? Some suggest a hidden disk of smaller icy objects, collectively exerting enough pull to mimic a single massive planet. Others propose we're seeing a statistical fluke, an illusion created by observational bias, where we've only mapped the most extreme orbits by chance. But the hunt is far from over. Next-generation telescopes like the Vera Rubin Observatory, with its panoramic view of the sky, could finally settle the debate. If Planet 9 exists, its infrared glow or reflected sunlight might betray its position. And if it doesn't, well, that's almost more thrilling because it means we're missing something even bigger in our understanding of how the solar system works. This isn't just about finding another planet, it's about rewriting the story of our cosmic neighborhood. Whether Planet 9 turns out to be a frozen super-Earth, a ghostly echo of past collisions, or just a tantalizing mathematical glitch, one thing's certain: the outer solar system still has secrets to spill. And somewhere out there, in the vast and silent dark, the truth is waiting. Look closely at the universe's grandest maps, and you'll see it not just galaxies sprinkled randomly, but a shimmering web of light and gas stretching across billions of light years. This is the cosmic web, the universe's hidden skeleton, and its delicate threads hold the answer to one of cosmology's deepest riddles: how does emptiness build structure? At its heart, the cosmic web is a network of filaments, tendrils of hydrogen gas so thin they'd make spider silk look bulky, yet so long they could bridge galaxies. These aren't just passive strings, they're cosmic highways funneling matter into galaxy clusters like rivers feeding an ocean. Simulations show that without this web, the universe would be a scattered mess, with galaxies adrift in a featureless void. Instead, gravity sculpted these filaments in the aftermath of the Big Bang, drawing matter into a labyrinth where walls of galaxies border yawning voids. But here's the twist: we can barely see them. These filaments are made of diffuse, ionized gas, glowing faintly in ultraviolet but often drowned out by starlight. It's like trying to spot a whisper in a hurricane. Only recently, with tools like the Hubble Space Telescope's Cosmic Origins spectrograph, have we caught glimpses, hints of hydrogen linking distant quasars, or the ghostly glow of intergalactic gas lit up by nearby starbursts. The real mystery lies in what these filaments do. They're not just scaffolding, they're active players in galactic evolution. Some theories suggest filaments act as fuel lines, feeding galaxies fresh gas to forge new stars. Others propose they're cosmic incubators, their gravitational pull triggering the collapse of gas clouds into galaxies. Then there's the dark matter factor. These threads likely trace unseen halos of dark matter, their gravity guiding the gas into these intricate patterns. Perhaps the most mind-bending realization: the cosmic web might be vibrating. Like plucked guitar strings, filaments could resonate with the echoes of ancient collisions, their oscillations subtly influencing how galaxies spin and cluster. Future telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope aim to map these vibrations, decoding the web's hidden symphony. For all its grandeur, the cosmic web humbles us. It's a reminder that even the emptiest corners of the universe are threaded with invisible order, a tapestry woven by gravity, dark matter, and time itself. And as we peel back its layers, we're not just studying structure, we're reading the universe's diary, written in gas and starlight, one filament at a time. They slip through your body by the trillions every second, ghostly, nearly weightless, and almost undetectable. Neutrinos are the universe's ultimate escape artists, capable of passing through light years of lead without a single collision. Yet these shadowy particles, once thought to be massless, hold a secret that could rewrite our understanding of reality. They do have mass, just not much. And that tiny whisper of weight might be the reason everything, stars, planets, us, exists at all. The mystery starts with how little they weigh. Neutrinos are at least 500,000 times lighter than electrons, the next lightest particles we know. Why so slight? One leading theory points to the Higgs field, the cosmic molasses that gives particles mass. Unlike electrons or quarks, neutrinos might only brush against this field lightly, like a feather skimming water, barely picking up any heft. But here's the catch: the standard model of particle physics never predicted neutrinos would have mass at all. Their weight, however minuscule, is a crack in the foundation of our most successful theory. Then there's the antimatter enigma. Every particle has an antimatter twin with opposite charge, and the Big Bang should have created equal amounts of both. Yet today, antimatter is vanishingly rare. Neutrinos might hold the answer. They're the only particles known to oscillate, changing between three flavors: electron, muon, and tau as they travel. This chameleon-like behavior suggests they could violate a sacred symmetry called CP invariance, where particles and antiparticles behave identically. If neutrinos favor matter over antimatter even slightly, they might have tipped the cosmic scales in our favor, allowing a universe of galaxies, not just empty radiation, to form. The challenge: catching them in the act. Detectors like Japan's Super Kamiokande, a tank filled with 50,000 tons of ultra-pure water, buried a kilometer underground, wait years to spot a handful of neutrino interactions. Even then, the data is maddeningly subtle. Recent experiments like T2K and NOVA have glimpsed hints of CP violation, but the signal flickers like a candle in a storm. What if solving this riddle requires something beyond the standard model? Theorists propose seesaw mechanisms, where ultra-heavy neutrinos we've yet to discover balance the light ones we know, or sterile neutrinos, phantom particles interacting only via gravity. Others wonder if neutrinos are Majorana particles, acting as their own antiparticles, a property that could explain their featherweight mass and matter's dominance. The stakes couldn't be higher. Unlocking the neutrino's secrets might reveal why the universe didn't annihilate itself at birth and expose entirely new physics hiding in plain sight. Future experiments like the Deep Underground Neutrino Experiment, DUNE, will fire beams of neutrinos 800 miles through Earth to study their oscillations with unprecedented precision. Every flicker, every shift in flavor, is a clue in a cosmic detective story where the prize isn't just knowledge, it's understanding why anything exists at all. One thing's certain: neutrinos refuse to play by the rules. They're cosmic riddles wrapped in quantum enigmas, so elusive we've barely scratched their surface. And somewhere in their ghostly dance, the universe might have left its biggest clue not in the stars, but in the shadows between them. In 1954, newspapers buzzed with an eerie headline: an unknown satellite was orbiting Earth and no nation claimed it. Dubbed the Black Knight, this phantom object quickly became space's most enduring urban legend. Some swore it was an ancient alien probe, silently watching us for millennia. Others insisted it was a relic of lost human technology, or even a piece of Nikola Tesla's forgotten experiments, catching and reflecting his early radio transmissions back to Earth. The truth, far stranger than fiction, and a perfect example of how easily cosmic myths take root when reality is just out of reach. The Black Knight's lore grew with each retelling. In the 1960s, ham radio operators reported odd delays in their signals, as if something in orbit was echoing them back. Then came the infamous 1998 NASA shuttle mission, where grainy footage appeared to show a dark, irregular object drifting near the ISS. Conspiracy theorists pounced, calling it proof of the Black Knight. Never mind that NASA identified it as a thermal blanket lost during a spacewalk. The human brain craves patterns, and in the vast, silent expanse of space, even debris can become a messenger from the stars. So what was the Black Knight? The most likely culprit is a mix of misidentified space junk and a dash of Cold War paranoia. Early radar echoes attributed to the satellite might have been stray reflections from the Discoverer satellites, a secretive U.S. reconnaissance program. Later sightings often traced back to known spacecraft or discarded rocket parts tumbling unpredictably in orbit. Yet the legend persists, fueled by the tantalizing possibility that we're not alone, and that evidence might be floating just overhead. The deeper irony: humanity has placed mysterious objects in orbit, like the enigmatic dark satellites used for classified missions. These real-world shadows, coupled with our love of a good mystery, keep the Black Knight alive in pop culture. From sci-fi novels to viral YouTube clips, it endures as a symbol of our cosmic curiosity and our tendency to see aliens where there's only aluminum and chance. Perhaps the Black Knight's greatest lesson isn't about aliens, but about us. In the void of space, where answers are scarce and imagination runs wild, even a stray bolt can become a relic of another world. And who knows, somewhere in the attic of the cosmos, there might still be artifacts waiting to be found. Until then, the Black Knight remains a celestial Rorschach test. What you see in it says everything about what you hope is out there. Look up at the western sky just after sunset, or the eastern horizon before dawn, and you might catch a ghostly glow stretching up from the horizon like a celestial pyramid of light. This is the Zodiacal light, one of the solar system's most hauntingly beautiful and least understood phenomena. For centuries, observers mistook it for the first hint of dawn or the lingering breath of twilight. But this eerie radiance comes from something far stranger: a vast diffuse cloud of dust grains, each no larger than a grain of pollen, drifting along the same plane where planets orbit the sun. The puzzle: we still don't know exactly where all this dust comes from. The leading suspects are comets, those icy wanderers that shed debris as they swing close to the sun, and asteroid collisions, which blast fragments into space like cosmic shrapnel. Yet when researchers tally up the potential contributions from known comets and asteroids, the math doesn't quite add up. There's more dust out there than these sources should produce, as if the solar system is hiding a secret factory churning out invisible particles. Some clues point to Mars as an unlikely accomplice. The planet's thin atmosphere and fierce dust storms might be launching grains into interplanetary space, where solar radiation pushes them into the ecliptic plane. Others argue Jupiter's gravity could be herding debris from the outer solar system inward, creating a steady drizzle of microscopic particles. Then there's the wild card: interstellar dust, swept up as the sun plows through the galaxy, though most of these intruders would be moving too fast to settle into the zodiacal cloud. The real intrigue lies in what this dust reveals about the solar system's hidden activity. Far from being a static relic, the zodiacal light might be a live feed of ongoing chaos: collisions we haven't witnessed, comets we haven't discovered, or even processes we haven't imagined. Recent studies suggest the dust cloud isn't perfectly smooth, but contains ripples and clumps, like footprints left by recent asteroid smash-ups or the ghostly trails of long-vanished comets. For all its subtlety, the zodiacal light holds cosmic significance. It's a reminder that even the empty spaces between planets are teeming with unseen motion, a delicate ballet of destruction and renewal playing out in sunlight too faint for the naked eye. Future missions like Japan's Destiny Plus aim to fly through this dust cloud, analyzing its composition to trace its origins. Until then, this ethereal glow remains a silent witness to the solar system's secrets, a luminous riddle written in specks of dust, waiting for us to decipher its story. Venus has always been the solar system's enigma, a world of crushing pressures, scorching temperatures, and clouds of sulfuric acid. But in 2020, astronomers dropped a bombshell: traces of phosphine, a gas that on Earth is almost exclusively linked to life, had been detected in its upper atmosphere. The discovery sent shockwaves through the scientific community. Here was a tantalizing possibility, a whiff of something biological floating in the most inhospitable place imaginable. Phosphine shouldn't exist on Venus, at least not in any significant amount. On Earth, it's produced by anaerobic bacteria thriving in oxygen-free environments like swamps and animal guts, or in labs through industrial processes. But Venus lacks factories and cows. The planet's extreme conditions should break phosphine apart almost instantly, meaning whatever's making it must be replenishing it constantly. So where's it coming from? The initial team, using data from the James Clerk Maxwell Telescope and the ALMA array, stood by their findings, ruling out known abiotic sources like volcanic eruptions or lightning. Venus volcanoes, while active, don't seem to erupt in ways that would produce enough phosphine, and the gas's concentration, about 20 parts per billion, was just high enough to raise eyebrows but low enough to evade easy dismissal. Skeptics, however, weren't convinced. Some questioned the data processing, suggesting the signal might be a false alarm caused by sulfur dioxide, a common Venusian gas that can mimic phosphine's spectral signature. Others proposed exotic chemistry, unknown reactions in Venus's acidic clouds, perhaps involving minerals lofted from the surface. There's even a wildcard theory. Micrometeorites constantly raining down on the atmosphere could theoretically spark phosphine formation, though no one's sure how efficiently. Then came the twist. Follow-up observations failed to confirm the original detection, leaving the scientific community in limbo. Was the phosphine real or just noise in the data? The debate crystallizes a fundamental challenge in astrobiology: how to interpret ambiguous signals from worlds we can't easily visit. Venus's thick clouds might hide microbial life floating in temperate layers, shielded from the worst of the heat below and the acid above. Or they might be stirring up chemical surprises we've yet to unravel. The stakes are higher than just one gas. If phosphine is biological, it redefines the habitable zone, proving life can thrive in places we once wrote off as hellish. If it's not, Venus becomes a laboratory for discovering new planetary chemistries, ones that might trick us again on distant exoplanets. Future missions like NASA Da Vinci and ESA Envision aim to probe the atmosphere directly, hunting for answers in the planet's corrosive skies. For now, the Venus phosphine mystery lingers, a reminder that even our nearest planetary neighbor can spring surprises that defy easy explanation. Whether it's microbes, minerals, or something stranger still, one thing's certain: Venus isn't done challenging our assumptions. And in that uncertainty lies the thrill of discovery, the chance that even the most hostile worlds might whisper secrets we're only beginning to hear. Mars should be a dead world, frozen, arid, and chemically inert. Yet something on the red planet keeps belching methane into its thin atmosphere, and we can't figure out what. This isn't just a steady leak, it's a series of erratic spikes, appearing and vanishing like a cosmic game of peekaboo. On Earth, methane is a calling card of life, produced by everything from cows to microbes, or geological activity like hydrothermal vents. So when rovers and orbiters started sniffing out these mysterious plumes, the question became unavoidable. Is Mars winking at us with hints of hidden biology, or are we witnessing geology stranger than we ever imagined? The first whiffs came in 2003, when the European Space Agency's Mars Express orbiter detected trace amounts of methane hovering over certain regions. Then, in 2013, NASA Curiosity rover hit the jackpot, a tenfold spike in methane levels that lasted weeks before dissipating. But here's the twist: when the European Russian Trace Gas Orbiter arrived in 2016 with more sensitive instruments, it found Nothing, not a trace. It was as if Mars had turned off the tap the moment we brought a better detector. This inconsistency is the heart of the riddle. Methane on Mars shouldn't linger long. UV radiation and chemical reactions should break it apart within a few hundred years, maybe even decades. So whatever's producing it must be active now, replenishing the gas in bursts we've yet to predict. One leading theory points to subterranean microbes, possibly buried deep where liquid water might still exist. On Earth, microorganisms called methanogens thrive in similar conditions, munching on minerals and exhaling methane. Could Martian microbes be doing the same beneath the rusty soil? But don't pack your alien hunting gear just yet. Geology offers compelling alternatives. Serpentinization, a process where water reacts with certain rocks like olivine, can produce methane without any biology involved. Mars has plenty of these minerals, and if pockets of subsurface water still exist, they could be fueling this reaction. There's also the wild card of clathrates, methane ice trapped in cage-like structures underground, occasionally releasing bursts when temperatures or pressures shift. The plot thickened in 2019 when Curiosity detected seasonal variations in background methane levels, rising in summer and fading in winter. This cyclical pattern suggests a reservoir of the gas slowly responding to environmental changes. But is it a vast underground store or something more localized? Some researchers propose the methane might be seeping from ancient fractures where it's been trapped for eons, while others wonder if dust storms play a role, stirring up the surface and releasing trapped gases. Then came the real curveball. In 2021, scientists realized some methane detections might overlap with Curiosity's own activities, specifically when the rover's wheels crushed rocks, potentially releasing trapped gas. Could we have been measuring our own disturbance? Yet this doesn't explain the orbital detections, leaving the debate wide open. The truth might lie in future missions. NASA Perseverance rover carries instruments to analyze methane with unprecedented precision, while the ESA's Rosalind Franklin rover, set to launch in 2028, will drill deeper than ever before. If either catches a spike in the act, they might trace it to its source, settling the debate once and for all. Until then, Mars methane remains a tantalizing riddle, a whisper of possibility that refuses to be ignored. Whether it's the breath of hidden life or the groan of ancient rocks, one thing's clear: the red planet still has secrets to spill, and with every erratic spike, it dares us to look closer, dig deeper, and stay curious. Saturn's moon Titan is a world straight out of science fiction, a place where rivers carve valleys into icy bedrock, where rain falls from hazy orange skies, and where vast lakes shimmer under the dim sunlight. But these aren't lakes of water. They're filled with liquid methane and ethane, hydrocarbons that would evaporate instantly on Earth yet pool freely on Titan's frigid surface. This is the only place in the solar system other than Earth with stable liquid on its surface, and it raises a fascinating question: how does Titan keep these lakes from vanishing into thin air? The answer lies in an alien water cycle unlike anything on Earth. Titan's atmosphere is thick with nitrogen and methane, creating a greenhouse effect that traps just enough heat to keep methane liquid at -180 degrees Celsius. But here's the twist: methane isn't just sitting there. It's constantly evaporating, forming clouds, and raining back down in a slow-motion loop that reshapes the landscape over millennia. Unlike Earth's water cycle, which operates on days or weeks, Titan's methane weather moves at a glacial pace, with storms that might last for years and droughts stretching centuries. Then there's the mystery of replenishment. If methane were only evaporating and raining back down, Titan's lakes should have dried up eons ago. something must be feeding them, and the leading suspect is a hidden network of underground reservoirs. Cassini's radar scans revealed that some lakes, like Ontario Lacus near the South Pole, have shorelines that rise and fall dramatically, suggesting liquid is seeping in and out of porous ice beneath the surface. It's as if Titan has a subterranean plumbing system, with methane filtering through cracks and caverns like groundwater on Earth. Seasonal shifts add another layer of intrigue. Titan's year lasts 29 Earth years, and as its poles tilt toward the sun, massive storms migrate across the moon, filling dry lake beds and carving new ones. In 2012, Cassini observed a sudden darkening near Titan's equator, a sign of methane rain falling in a region that had been bone dry for years. This wasn't just weather, it was proof of a dynamic climate, one that reshapes the surface in ways we're only beginning to map, but the real jaw-dropper. Titan's lakes might hold clues to Earth's own past. Billions of years ago, before oxygen filled our atmosphere, our planet could have been shrouded in similar hydrocarbon haze, with methane playing the role water does today. Or, in a chilling twist, Titan might mirror Earth's distant future, a frozen world where the last vestiges of liquid huddle at the poles, waiting for the sun's inevitable expansion to boil them away. What's certain is this: Titan's lakes are more than just puddles. They're windows into the extremes of planetary science, proving that even in the coldest corners of the solar system, nature finds a way to defy expectations. And as future missions like Dragonfly prepare to explore this alien world up close, one thing's clear: the universe's playbook for chemistry, weather, and maybe even life is far more creative than we ever imagined. Beneath Enceladus's icy crust, a cosmic fountain is erupting, one that shouldn't exist. This tiny moon of Saturn, barely 500 kilometers across, is spewing towering geysers of water vapor and ice crystals into space, creating a shimmering halo around itself. These plumes aren't just a dazzling spectacle, they're a direct pipeline to a hidden ocean, a secret world buried under kilometers of ice. And what's gushing out isn't just water, it's a cocktail of organic molecules, salts, and even silica nanoparticles, the kind that on Earth only form near scalding hydrothermal vents. That's what makes Enceladus one of the most promising places to hunt for life beyond our planet. The discovery came in 2005, when NASA Cassini spacecraft caught the plumes in action near Enceladus's south pole. At first, scientists assumed these were just surface frost vaporizing under sunlight, but Cassini's daring dives through the plumes revealed something far more extraordinary. They were shooting out at speeds exceeding 1,600 kilometers per hour, carrying not just ice but methane, carbon dioxide, and ammonia, ingredients essential for life as we know it. Even more startling, the plumes contained molecular hydrogen, a chemical signature that on Earth often points to active hydrothermal systems where microbes thrive in total darkness. It was as if Enceladus had rolled out a welcome mat for astrobiologists, offering free samples of its subsurface ocean without us needing to drill through the ice. So what's powering these eruptions? The leading theory points to tidal heating. Enceladus orbits Saturn in a stretched, elliptical path, and every time it swings closer to the planet, Saturn's gravity squeezes and stretches the moon's interior like a stress ball. This constant flexing generates enough heat to keep a global ocean liquid beneath the ice and creates cracks called tiger stripes near the South Pole where water bursts through. But here's the catch: calculations suggest tidal heating alone shouldn't produce this much energy. Some researchers speculate the ocean might be enriched with antifreeze like ammonia, lowering its freezing point. Others wonder if Enceladus's core is porous, allowing water to percolate down and react with minerals, releasing extra heat through chemical reactions. Then there's the life question. The plume's silica particles strongly suggest hydrothermal activity, think Yellowstone's geysers, but on an alien moon. On Earth, such environments teem with extremophiles, organisms that thrive in scorching, mineral-rich waters. Could similar microbes be thriving in Enceladus's dark depths, feeding on hydrogen and belching out methane? The challenge is that without a direct sample, we're left reading tea leaves. Future missions like NASA proposed Enceladus Orbolander aim to analyze plume material with advanced instruments, hunting for amino acids or even cellular structures. The wildest possibility, Enceladus's ocean might be older than Earth's. Some models suggest its liquid water has persisted for billions of years, offering a stable cradle for life to emerge and evolve. That raises a haunting prospect. If life exists there, it might have had a head start on us. Every icy grain spewed into space could carry clues, and with no destructive atmosphere or radiation to scramble them, those clues might be perfectly preserved. What makes Enceladus unique isn't just its hidden ocean, it's the moon's generosity. Unlike Europa or other icy worlds, it delivers its secrets directly to us, spraying them into space where any passing spacecraft can scoop them up. In a universe where most mysteries stay locked away, Enceladus is an open book, its pages written in geysers of ice and whispers of molecular hydrogen. All we have to do is turn the page. Beneath Europa's frozen, cracked surface lies one of the most tantalizing secrets in our solar system, a vast, global ocean containing more than twice the volume of all Earth's seas combined. This isn't just any ocean. It's a salty, swirling abyss wrapped in an icy shell up to 24 kilometers thick, kept liquid not by sunlight but by the relentless gravitational kneading of Jupiter and its other moons. Every orbit stretches and squeezes Europa like a cosmic stress ball, generating enough internal heat to maintain this hidden sea for billions of years. And where there's liquid water, energy, and organic chemistry, there's potential for life as we know it, or perhaps life as we don't. What makes Europa's ocean so extraordinary isn't just its existence, but its intimacy with the moon's rocky core. On Earth, oceans and seafloor are separated by miles of water, but Europa's sea likely brushes directly against mineral-rich rock, creating a sprawling network of hydrothermal vents. These underwater geysers, spewing superheated, chemical-laden fluids, are oases for extremophiles on our planet, organisms that thrive in crushing pressures and total darkness. If similar vents exist on Europa, they could be fueling entire ecosystems we've yet to imagine. The Hubble Space Telescope has even detected plumes of water vapor erupting from Europa's icy crust, offering free samples of what might lurk below. Yet for all its promise, Europa presents staggering challenges. Its surface is bombarded by Jupiter's intense radiation, frying anything unprotected within hours. The ice shell itself is a dynamic, shifting labyrinth, with regions where it might thin to just a few kilometers, allowing ocean water to well up and refreeze in chaotic, jumbled patterns called chaos terrains. These areas, like the famous Connemara chaos, could be natural skylights into the ocean below, or treacherous zones where any lander might sink into a briny slush. The real breakthrough will come when we can taste Europa's ocean directly. NASA's upcoming Europa Clipper mission, launching in 2024, will conduct dozens of close flybys, mapping the ice shell and analyzing plume material with precision. Even more ambitious is the proposed Europa lander, which would drill or melt through the ice to deploy a submersible, a technological feat akin to sending a robot to another planet's ocean floor. The engineering hurdles are immense. How to sterilize the probe to avoid contaminating Europa with Earth microbes, how to power it in perpetual darkness, and how to communicate through kilometers of ice. But the potential rewards are cosmic. If life exists in Europa's abyss, it might resemble Earth's deep-sea vent organisms, or be something wholly alien, adapted to conditions we can barely replicate in labs. Some theories suggest Europa's ocean could harbor slow-moving, gelatinous creatures buoyed by low gravity, or even silicon-based life forms exploiting sulfur compounds instead of oxygen. Others caution that the ocean might be lifeless but chemically rich, a frozen snapshot of Earth's primordial seas before biology took hold. The deeper mystery is how life could arise in such isolation. Earth's oceans are connected to the atmosphere and bathed in sunlight, but Europa's ecosystem, if it exists, would rely entirely on geology and chemistry, a closed loop of energy and matter. That makes it the ultimate test case for whether life is a cosmic imperative or a rare fluke. Every plume we analyze, every radar echo we interpret, brings us closer to answering whether we share the solar system with neighbors, or whether, in Europa's dark waters, we're seeing the reflection of our own loneliness. One thing's certain, Europa's ocean is more than a scientific curiosity. It's a mirror held up to our deepest questions about life's resilience and diversity. As we prepare to probe its depths, we're not just exploring a moon, we're testing the boundaries of what's possible in the universe. And whether we find microbes or marvels, the discovery will rewrite our place in the cosmos. The ice may hide the answers, but it's already begun to crack. Ceres, the largest object in the asteroid belt, hides a dazzling mystery in its cratered surface, bright spots so reflective they gleam like cosmic beacons against the dwarf planet's dark, rocky terrain. The most famous cluster, nestled inside Kuiper crater, shines with the intensity of a spotlight, visible even to amateur telescopes. At first glance, they might look like patches of snow or ice, but the truth is far stranger. These luminous marks are made of sodium carbonate, a type of salt arranged in such pure, concentrated deposits that they act like celestial mirrors, bouncing sunlight back into space with eerie efficiency. How did these salty stains end up on a barren world like Ceres? The leading theory points to cryovolcanism, a slow-motion eruption of briny water from deep beneath the surface. Imagine not molten rock, but a slushy mix of water, salts, and ammonia bursting through cracks in the crust, then freezing instantly in the vacuum of space. Over time, repeated eruptions could have built up these gleaming deposits, like layers of frost on a winter window. NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, found evidence supporting this idea. The bright spots sit atop domes and fractures, geological fingerprints of upward-moving fluids. Even more tantalizing, Dawn detected traces of organic molecules nearby, hinting at a complex chemistry brewing beneath the surface. But cryovolcanoes aren't the only suspects. Some scientists argue impacts could have unlocked these salty treasures. When a massive asteroid slammed into Ceres, forming Kuiper crater 20 million years ago, the collision might have fractured the crust, tapping into a subterranean reservoir of brine. The sudden release of pressure would send this salty slurry spraying across the crater floor, where it would crystallize into the shimmering patches we see today. Supporting this, the brightest spots cluster in the crater's center, ground zero for the most violent upheaval. Then there's the wild card: could Ceres still be active? Dawn spotted a faint, intermittent haze hovering over Kuiper crater, possibly water vapor escaping from lingering pockets of subsurface brine. If so, the bright spots might not be ancient relics but living features, still evolving as hidden liquids seep to the surface. This would make Ceres one of the few places in the solar system with ongoing geological activity, a frozen world with a surprisingly dynamic heartbeat. What makes these spots so captivating isn't just their origin, it's what they represent. Ceres was once written off as a boring, inert rock, but these gleaming deposits reveal a world with a hidden water cycle, one that might have persisted for billions of years. They're a reminder that even the smallest bodies in our cosmic neighborhood can harbor secrets as profound as those of gas giants or icy moons. And as future missions, like the proposed Ceres sample return, aim to bring pieces of this salty puzzle back to Earth, one thing's clear: the asteroid belt's largest resident isn't just a relic of the past. It's a world with stories still left to tell, written in light and salt, waiting for us to decipher them. Neptune's moon Triton shouldn't be alive, yet somehow it's erupting like a cosmic geyser. This frozen world, barely larger than Pluto, spews towering plumes of nitrogen gas 8 kilometers high into its wispy atmosphere, creating dark streaks across its icy surface. It's the coldest known object in our solar system, with temperatures plunging to -235 degrees Celsius, so cold that nitrogen freezes solid like rock. Yet despite this deep freeze, Triton remains geologically active, a puzzle wrapped in frost that defies everything we know about how distant moons behave. The first clues came in 1989, when Voyager 2 captured images of these bizarre eruptions during its fleeting flyby. The plumes weren't volcanic in the traditional sense, no lava, no molten rock, but cryovolcanic, driven by substances that would be gases or liquids on Earth but behave like sluggish fluids or even solids in Triton's extreme cold. What's shocking is the energy source. Unlike Jupiter's moons Io and Europa, which get heated by gravitational tug-of-wars, Triton orbits Neptune in a near-perfect circle, eliminating tidal friction as a major heat source. So how does this captured Kuiper Belt refugee, billions of years old, still have the energy to erupt? One possibility lies beneath Triton's crust, a hidden ocean of ammonia-rich water kept liquid by antifreeze-like compounds. As Triton gradually cools from its violent capture by Neptune's gravity, this subsurface slush might be releasing bursts of pressurized nitrogen through cracks in the ice, like shaking a soda can and popping the tab. Another theory points to seasonal changes. Triton's poles take turns facing the sun during its 82-year seasonal cycle, and when sunlight penetrates its translucent nitrogen ice, it could be warming darker material trapped underneath, building pressure until the surface literally blows its top. Then there's the elephant in the room: Triton's backward orbit. Unlike nearly every other large moon in the solar system, Triton circles Neptune in the opposite direction of the planet's rotation, a glaring sign it didn't form there but was captured. This cosmic kidnapping would have been catastrophic, with gravitational interactions likely melting Triton's interior and stripping away any original moons Neptune might have had. The aftermath could have left Triton with a reservoir of heat that's still slowly leaking out, powering its geysers billions of years later. What makes Triton truly unique is its surface chemistry. The plumes carry not just nitrogen but methane, which under Triton's weak sunlight cooks into Tholen's complex organic compounds that paint the moon's surface pinkish red. These same molecules are found on Pluto and other Kuiper Belt objects, hinting at a shared lineage. But here's the kicker: some models suggest Triton might have been part of a binary system before Neptune snatched it, with the other body ejected into interstellar space, making Triton a cosmic orphan with a violent past. Future missions like NASA's Trident proposal aim to map Triton's plumes in detail, searching for clues to its subsurface ocean and capture history. Until then, this frosty enigma remains a testament to the solar system's capacity for surprise, a world that by all rights should be geologically dead, yet somehow keeps sputtering to life, proving that even in the darkest, coldest reaches, the universe refuses to play by our expectations. Deep in the frigid reaches of the Kuiper belt, a cosmic oddity spins faster than a blender on full power Haumea, a dwarf planet shaped like a squashed football, racing through a full rotation every 4 hours. But that's not even the strangest part. In 2017, astronomers witnessed something unprecedented during a stellar occultation, a thin, dark ring circling Haumea's waist like a celestial hula hoop. This made Haumea the first known dwarf planet with rings, and one of only 5 ringed worlds in our solar system. The question is, how does a tiny, distant object barely 700 kilometers wide hold onto a ring system, while giants like Pluto and Eris don't? The leading theory points to a violent past. Haumea's bizarre shape and blistering spin suggest it survived a cataclysmic collision billions of years ago, a smash-up so powerful it shattered the original body, leaving behind Haumea, its 2 moons Hioka and Namoka, and likely a cloud of debris. Normally, this debris would either coalesce into new moons or drift away, but Haumea's rapid rotation might have created a gravitational sweet spot, a place where particles could settle into a stable ring, suspended between the tug of the dwarf planet and the outward push of its spin. It's a delicate balance, like spinning a bucket of water fast enough to keep it from spilling. Yet collisions alone don't explain everything. Saturn's dazzling rings are constantly refreshed by moonlets breaking apart, while Jupiter's faint rings are fed by dust kicked up from meteorite impacts. Haumea's ring, by contrast, is pristine and narrow, more like a trimmed hedge than a scattered debris field. This suggests something else is at work, perhaps an unseen shepherd moon, too small to detect from Earth, gently herding the particles into place. Or maybe Haumea's unusual composition plays a role. Unlike most Kuiper belt objects, which are icy and porous, Haumea is dense and rocky, with a surface of almost pure crystalline water ice. This could create unique electrostatic or gravitational conditions that trap ring particles in ways we don't yet understand. The real puzzle isn't just how Haumea's ring formed, but why others don't have them. After all, if Haumea could do it, why not Pluto or Makemake? One possibility is timing. Haumea's collision might have happened recently, cosmically speaking, leaving its ring too young to have dissipated. Alternatively, Haumea's extreme spin might be the key. Most Kuiper belt objects rotate far more slowly, lacking the centrifugal force to keep debris from clumping into moons. It's also possible we've just missed other rings. Detecting them requires perfect alignments where distant objects pass in front of stars, casting shadows that reveal their secrets. Until 2017, no one thought to look for rings around anything but planets. What makes Haumea's ring so thrilling is what it implies about the solar system's small bodies. We used to think of them as inert fossils, frozen in time since the solar system's birth. But Haumea proves they're dynamic worlds sculpted by violence, shaped by gravity, and capable of surprises that defy textbook definitions. Future missions, like the proposed interstellar probe, might one day visit Haumea up close, settling the debate once and for all. Until then, this spinning, ringed oddity stands as a reminder. Even in the farthest corners of our cosmic neighborhood, the universe loves breaking its own rules. Out beyond Neptune, where the solar system's rulebook seems to fray at the edges, an icy loner named Sedna traces a path so stretched it defies logic. This dwarf planet, smaller than Pluto but just as mysterious, takes 11,000 years to complete a single, lopsided orbit around the Sun, swinging from 76 astronomical units at its closest to a staggering 936 at its farthest. That's so distant, the Sun would appear as little more than a bright star in its frozen sky. The real puzzle, Sedna never gets close enough to Neptune for the ice giant's gravity to explain its bizarre trajectory. It's as if something or someone gave it a cosmic kick, sending it spiraling into the void with no clear explanation. Theories abound, but none fit perfectly. The leading suspect is a long-lost sibling of the Sun, a rogue star that brushed past our solar system billions of years ago, yanking Sedna outward like a gravitational slingshot. Computer simulations show this could work, but there's a catch. The passing star would have needed to come uncomfortably close, within about 800 astronomical units, to fling Sedna so far without tearing it away entirely. That's a cosmic near miss by astronomical standards, and we've found no stellar remnants nearby to prove it happened. Then there's the Planet 9 hypothesis. If a massive, undiscovered world lurks in the outer darkness, its gravity could have sculpted Sedna's orbit over eons, nudging it into this extreme ellipse without ever revealing itself. Sedna isn't alone in this odd behavior. A handful of other distant objects, like the aptly named Goblin, share similar tilted, elongated paths. Together, they form a scattered chorus of clues hinting at an unseen conductor orchestrating their motions. But until we spot Planet 9, this remains an elegant guess with no smoking gun. Perhaps the strangest twist is Sedna's red hue, deeper than Mars and rivaling some of the most ancient objects in the solar system. This suggests its surface has been baked by cosmic rays for eons, untouched by the geological refresh button that erases such stains on active worlds. Yet Sedna's color is uneven, with patches of brighter material that might be fresh ice exposed by recent impacts or even cryovolcanism. How could a body so small and distant still harbor geologic activity? Unless, of course, it's not as alone out there as it seems. Sedna's isolation raises existential questions. If it was born in the crowded disk of the early solar system, how did it end up so detached? Some models suggest it might be a stolen relic, a captured citizen of another star system, adopted during the Sun's infancy when stellar nurseries were packed tight. Others propose it's a survivor of a shattered larger body, its orbit a frozen record of some primordial collision we've yet to piece together. Every new observation deepens the intrigue. Recent studies hint that Sedna's orbit might be influenced by the Milky Way's own gravity, a subtle tug from the galaxy's dark matter halo that gently perturbs distant objects over millions of years. It's a reminder that the solar system doesn't end at Pluto or even the Kuiper belt. It's a dynamic web of forces stretching far into the interstellar dark, where objects like Sedna drift like messages in bottles, waiting for us to decode their stories. One thing's certain, Sedna's lonely dance challenges the tidy narrative of our solar system's history. Whether it's a victim of stellar theft, a pawn of Planet 9, or a witness to some forgotten cataclysm, its orbit is a cosmic riddle written in ice and time. And until we solve it, Sedna will keep its secrets, looping silently through the dark, a ghost from the solar system's violent youth. In the late 1800s, astronomers were convinced the solar system held a hidden world, a tiny, scorched planet lurking inside Mercury's orbit. They called it Vulcan, named after the Roman god of fire, and for decades, respected scientists reported fleeting glimpses of this phantom world crossing the sun's face. The motivation wasn't just curiosity. Mercury itself was misbehaving. Its orbit wobbled in ways Newton's gravity couldn't explain, and Vulcan seemed the perfect culprit, a small but mighty gravitational tugger hiding in the solar glare. Even the great Urbain Leverrier, who'd predicted Neptune's existence using orbital math, championed Vulcan's reality. But here's the twist: Einstein killed Vulcan without ever looking through a telescope. His theory of general relativity, published in 1915, solved Mercury's orbital quirks elegantly. The Sun's immense mass, Einstein showed, warps spacetime so profoundly that Mercury's path isn't a perfect ellipse but a slowly rotating spiral. no invisible planet required. Case closed, not quite. While Vulcan as originally imagined was debunked, modern astronomers have revived the hunt for intra-Mercurial objects, armed with tools Leverrier couldn't have dreamed of. The difference: today's searches aren't for a full-fledged planet, but for elusive asteroid swarms or exotic micro-worlds surviving in the solar furnace's glare. Some clues suggest they might be out there. The Parker Solar Probe, skimming closer to the Sun than any spacecraft before it, has detected unexpected dust-free zones near Mercury's orbit, regions where gravitational forces or intense heat should have cleared debris, but the patterns don't quite match predictions. Could unseen bodies be shepherding this dust? Then there's the Vulcanoid hypothesis, a theoretical population of asteroids stabilized by Mercury's gravity, orbiting so close to the Sun that they're nearly impossible to spot against its brilliance. These wouldn't be the sprawling, Earth-like world 19th century astronomers envisioned, but rugged, charcoal-black rocks, baked barren over billions of years. The challenge is catching them. Observing anything near the Sun requires precision timing, like spotting a moth against a floodlight during a brief blackout. NASA's Stereo spacecraft, designed to study solar activity, has doubled as a Vulcanoid hunter, scanning for reflections off hypothetical asteroids during solar eclipses. So far, nada, but absence of evidence isn't evidence of absence. Some models suggest any surviving Vulcanoids would be smaller than Manhattan, their orbits chaotic over geologic time, making them cosmic needles in a haystack of solar radiation. Why keep searching? Because Vulcan's ghost represents more than a historical curiosity. Finding even a pebble where physics says it shouldn't be could reveal gaps in our understanding of orbital dynamics or the solar system's violent youth. And there's poetic justice in the idea that Einstein's triumph over Vulcan might one day be nuanced by the discovery of something not a planet, perhaps, but a fragment of the story we're still piecing together. After all, the universe has a habit of hiding its wildest truths just beyond the edge of our theories. So while Vulcan the planet may be dead, the spirit of the hunt lives on, a reminder that sometimes the most enduring mysteries aren't about being right or wrong, but about asking the question at all. Our Sun seems solitary, a golden sentinel adrift in the cosmic dark. But what if it's not alone? Lurking in the shadows of scientific speculation is Nemesis, a hypothetical stellar companion so elusive it's been called the universe's best ghost story. The theory goes like this: roughly every 26 million years, Earth's fossil record shows catastrophic extinction events, dinosaurs being the most famous victims. In the 1980s, astronomers proposed a radical explanation: a dim, distant star orbiting our Sun in a vast, elliptical loop, periodically barging into the Oort cloud and hurling comets toward the inner solar system like a cosmic cue ball. They named this phantom Nemesis after the Greek goddess of retribution, a fitting title for a celestial reaper. The allure of Nemesis isn't just its drama, it's the eerie precision of those extinction cycles. Paleontologists have painstakingly mapped mass die-offs aligning with asteroid impacts and volcanic upheavals, but the timing's regularity begs for a grander culprit. Nemesis, if real, would be a red dwarf or brown dwarf, too faint for telescopes of the 80s to spot. Its orbit, stretching thousands of times farther than Pluto's, would take it a quarter of the way to the nearest star before swinging back for another pass. Each homecoming would destabilize icy debris at the solar system's edge, triggering showers of comets capable of sterilizing planets. Yet decades of searching have turned up empty. Infrared surveys like WISE, the Wide Field Infrared Survey Explorer, scanned the skies for Nemesis's heat signature, finding nothing matching the theory's predictions. Critics argue the extinction pattern itself might be statistical noise, a fluke of how we slice Earth's geological timeline. Others suggest alternative triggers, the solar system's rhythmic passage through dense spiral arms of the Milky Way, where interstellar clouds could perturb the Oort cloud without requiring a hidden star. But here's where the mystery deepens. While Nemesis remains missing, modern astronomy has uncovered a trove of binary and even trinary star systems, proof that solo stars like our Sun aren't the rule. Free-floating rogue planets and brown dwarfs, invisible to optical telescopes, wander the galaxy in surprising numbers. Could Nemesis be one of these, its orbit so stretched we've yet to cross its path? Or perhaps it's not a star at all, but a primordial black hole, its gravity tugging on the Oort cloud without emitting light. The most tantalizing clue might lie in the Kuiper belt. Strange orbital alignments among distant objects like Sedna hint at an unseen gravitational influence, though whether it's Nemesis, Planet 9, or something else entirely remains unclear. Future telescopes like the Vera Rubin Observatory could settle the debate by mapping the outer solar system's structure with unprecedented clarity. Until then, Nemesis lingers at the edge of science and myth, a reminder that sometimes the most compelling stories aren't about what we've found, but what we've yet to discover. Whether Nemesis exists or not, its legend endures because it speaks to a deeper truth. The universe loves to hide its secrets in the last places we'd think to look. And in that tension between hypothesis and evidence, between pattern and chaos, lies the thrill of the hunt, the chance that one day we might turn over the right cosmic stone and find the unexpected staring back. KIC 8462852, better known as Boötes star or Tabby star, doesn't flicker like a typical star. It doesn't dim in predictable planet-sized increments. Instead, it plunges into darkness erratically, sometimes dropping in brightness by a staggering 22% before lurching back to normal. Imagine a light bulb that randomly fades to a faint glow, then flares to full strength with no discernible rhythm. That's the enigma of Tabby star, a cosmic anomaly so baffling it sparked everything from cautious astrophysics papers to wild speculation about alien megastructures. The mystery began when NASA, a Kepler space telescope, designed to hunt for exoplanets by spotting the telltale dips caused by orbiting worlds, caught Tabby star behaving like nothing else in its database. Most planet-caused dimming events are symmetrical and repeat like clockwork, but this star's light curves were chaotic, steep, jagged drops lasting days or weeks, followed by long stretches of eerie stability. The most dramatic event, a series of dips in 2017 where the star's light plummeted in a way no natural phenomenon could easily explain. It wasn't just a single object blocking the light. It was as if something fragmented, something vast and uneven, was drifting across the star's face. Dust seems the most plausible culprit. Observations show the dimming is wavelength dependent, meaning shorter wavelengths of light are blocked more than longer ones, a classic fingerprint of fine particles scattering starlight. But even this theory has holes. The dust would need to be incredibly clumpy and dynamic to create such irregular patterns, and no known natural process produces dust clouds this erratic. Comets, a family of them, could theoretically break apart near the star, creating a swirling debris field, but the scale required would be unprecedented. A recent collision between planets might explain it, but the timing would have to be cosmically impeccable for us to catch the aftermath. Then there's the elephant in the room, the Dyson swarm hypothesis. Proposed by astronomer Jason Wright, the idea suggests an advanced civilization could build a network of energy collecting structures around their star, harnessing its power. These megastructures wouldn't need to be solid shells. They could be loose arrays of orbiting panels, occasionally blotting out light as they pass. It's a sci-fi concept rooted in real physics, and while it's a last resort explanation, Tabby's star's refusal to fit natural models keeps it on the table. The real intrigue lies in what we haven't seen. Unlike most variable stars, Tabby's star shows no excess infrared radiation, which you'd expect from warm dust. Its long-term dimming historical data suggests it's faded by about 14% over the past century, adds another layer of confusion. Could it be undergoing some rare phase of stellar adolescence, or is something else systematically obscuring our view? Future telescopes like the James Webb Space Telescope might analyze the dust's composition or spot hidden companion stars. Until then, this celestial rebel remains a masterclass in scientific humility. It's a reminder that the universe doesn't owe us tidy answers sometimes. The most profound discoveries come from the anomalies that refuse to fit the mold. Whether the answer is dust, aliens, or something stranger still, Tabby's star has already taught us one vital lesson. When the cosmos throws a curveball, that's when the real science begins. In April 2019, astronomers with the Breakthrough Listen project detected something unusual, a narrowband radio signal, precisely 982 MHz, emanating from Proxima Centauri, our closest stellar neighbor. This wasn't just any blip. The signal, dubbed BLC-1, checked several boxes for potential artificial origin. It appeared only when the telescope was pointed at the star, drifted in frequency as you'd expect from a transmitter on a moving planet, and occupied a quiet slice of the radio spectrum where natural cosmic noise is minimal. For a brief, electrifying moment, it seemed humanity might have stumbled upon a cosmic hello from just 4.2 light-years away. But here's the catch: Proxima Centauri isn't just any star. It hosts at least 2 planets, one of which, Proxima b, orbits in the habitable zone where liquid water could exist. The idea of a technologically advanced civilization right next door, close enough that a two-way conversation might take less than a decade, sent imaginations into overdrive. Was this the moment we'd dreamed of since the dawn of radio astronomy? The signal's timing was almost poetic, arriving just as the world grappled with a pandemic, offering a distraction that felt ripped from a sci-fi novel. Yet science thrives on skepticism. As researchers dug deeper, the story grew murkier. BLC-1 didn't repeat, a red flag for artificial signals, which are typically persistent or deliberately broadcast in patterns. Then came the kicker. Further analysis suggested the signal likely originated from human technology, possibly a malfunctioning satellite or even ground-based interference reflected off a passing aircraft. The telltale clue: subtle harmonics in the signal structure, fingerprints of earthly electronics rather than extraterrestrial engineering. But don't dismiss this as just another false alarm. The Proxima signal taught us something profound. Our detection methods are improving. BLC-1 was spotted not by chance, but by an AI sifting through terabytes of data, flagging anomalies human eyes might miss. This is the new frontier of SETI machine learning algorithms trained to distinguish between cosmic static, human-made noise, and the elusive needle in a haystack signal that might one day change everything. The real intrigue lies in what comes next. Proxima Centauri remains a prime target, not just for its proximity, but because of its rocky, potentially habitable world. Future telescopes like the Square Kilometre Array will listen with even greater precision, while projects like Breakthrough Starshot aim to send tiny probes hurtling toward the star within our lifetime. Whether BLC-1 was a cosmic whisper or a mundane glitch, it's a reminder that the universe keeps teasing us with possibilities, and that the next signal might not be so easy to explain away. So while we haven't found aliens yet, the hunt is far from over. Every false alarm sharpens our tools, refines our questions, and brings us closer to the day when a signal doesn't fade into static, but changes everything we think we know about our place in the cosmos. Until then, Proxima Centauri keeps its secrets, a silent neighbor with stories we're only beginning to decode. At the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, telescopes have detected something that shouldn't be there, a relentless flood of gamma rays, the universe's most energetic light pouring from the Milky Way's core. Dubbed the galactic center excess, this mysterious radiation glows far brighter than known sources like pulsars or gas clouds can explain. It's as if the universe left its high beams on in the cosmic basement, and no one knows who or what flipped the switch. The leading suspect, dark matter. Theorists propose that when these invisible particles collide, they might annihilate each other in bursts of gamma radiation. The Milky Way's core, packed with dark matter's gravitational pull, would be the perfect place to spot such fireworks. Simulations show certain dark matter models, like weakly interacting massive particles WIMP, could produce a signal eerily similar to what we observe. But there's a hitch: the gamma rays aren't distributed quite right. If dark matter were the culprit, the glow should be smooth, yet the excess appears clumpy, like scattered spotlights rather than a uniform haze. Enter the pulsar argument. Millisecond pulsars, rapidly spinning neutron stars, also emit gamma rays, and the galactic center teems with these ancient stellar corpses. Could unresolved pulsars, too faint to spot individually, collectively fake the excess? Some studies suggest so, noting that Fermi telescope data reveals faint point sources hiding in the noise. But critics counter that there simply aren't enough pulsars to account for the signal's intensity. It's like trying to explain a bonfire with a handful of matchsticks. The plot thickens when you consider the excess's shape. Unlike typical dark matter halos, which should be spherical, the gamma-ray glow is slightly flattened, as if squeezed by an invisible hand. Some researchers propose exotic physics, like dark matter interacting with itself through unknown forces, could warp the signal. Others wonder if we're seeing the aftermath of a long-ago galactic catastrophe, like a dwarf galaxy devoured by the Milky Way, its dark matter core still smoldering with annihilation. Then there's the wild card: primordial black holes. These hypothetical relics from the Big Bang could lurk in the galactic center, gobbling up matter and spewing gamma rays as they feed. Or perhaps the excess is a cosmic mirage, the combined glow of rare stellar processes we've yet to discover. The truth might lie in future telescopes, like the Cherenkov Telescope Array, which will map gamma rays with unprecedented resolution. For now, the galactic center excess remains a tantalizing riddle, a reminder that even in our own backyard, the universe keeps its most profound secrets hidden in plain sight. Whether it's dark matter's dying whisper or a chorus of unseen pulsars, one thing's certain: the answer won't just solve a puzzle, it could rewrite the rules of the cosmos. Imagine a universe where matter doesn't behave like particles or waves, but as something entirely different, an ethereal substance that defies our standard definitions of mass and energy. This is the radical premise behind unparticle physics, a theory so speculative it blurs the line between brilliant insight and mathematical daydream. Proposed in 2007 by physicist Howard Georgi, the idea suggests hidden sectors of reality where particles don't act like discrete objects, but instead manifest as unparticles, entities with fractional, ghostly properties that change depending on how you observe them. At its core, unparticle theory emerges from the possibility of extra dimensions, invisible layers of reality where familiar physics breaks down. In these hidden realms, particles might not have fixed masses but exist in a strange quantum haze, their properties smeared across space like a cosmic watercolor. The math behind this predicts bizarre behavior. unparticles wouldn't follow the clean energy levels we see in atoms, but would instead interact in continuous, fluid spectra. Picture trying to measure a rainbow where the colors blend seamlessly without distinct bands. That's the challenge unparticles pose to our measurement tools. Why should we care about such an abstract idea? Because unparticles could be the missing link to some of cosmology's greatest puzzles. Dark matter, for instance, might not be made of traditional particles at all, but of unparticle condensates, invisible, non-clumping halos that gravitationally sculpt galaxies without otherwise interacting. Even the accelerating expansion of the universe could get a fresh explanation. Unparticle fields might permeate space, exerting a gentle push that mimics dark energy's effects. Critics, however, aren't sold. Without experimental evidence, unparticle physics risks becoming a theory of everything and nothing, elegant equations with no tangible fingerprints. Particle colliders like the LHC have searched for unparticle signatures in high-energy collisions, but so far, no anomalous energy distributions or unexpected particle decays have emerged. Some argue the theory is too flexible, able to explain any observation post hoc without making testable predictions. Yet the most compelling aspect of unparticles isn't their potential to solve existing mysteries, it's the door they open to entirely new physics. If real, they'd force us to rewrite quantum field theory, redefine mass, and rethink the very nature of reality. Future experiments like ultra-precise neutron scattering studies or next-generation colliders might finally catch a glimpse of these phantom entities. Until then, unparticle physics remains a tantalizing what-if, a reminder that the universe's strangest truths often lurk just beyond the edge of our imagination. What if everything you've ever known, every star, every atom, every heartbeat was nothing more than lines of code in an unfathomably advanced simulation? This is the simulation argument, a modern cosmic riddle that blurs the line between philosophy and physics, forcing us to confront the unsettling possibility that reality might not be what it seems. The idea isn't new. Plato's cave hinted at illusions masking truth, but today's version comes with a Silicon Valley twist. Tech mogul Elon Musk famously put the odds at 1,000,000,000 to 1 that we're living in base reality, while philosopher Nick Bostrom formalized the argument with a chilling trilemma. Either civilizations never reach post-human computing power, they choose not to run ancestor simulations, or we're almost certainly living in one. The logic is deceptively simple. If advanced civilizations could create hyper-realistic simulations of conscious beings, think entire universes rendered in quantum bits, why wouldn't they? And if they did, the number of simulated minds would dwarf biological ones, making it statistically likely we're among the digital constructs. Scientists have even proposed ways to test the hypothesis, like hunting for pixelation in the fabric of space-time or glitches in quantum mechanics, a cosmic blue screen of death. Some theorists point to the oddly mathematical nature of physics itself as potential evidence. Why do particles follow precise equations unless they're programmed to? Even quantum indeterminacy, where particles exist in probability clouds until observed, feels eerily like a rendering optimization, a universe only simulating details when someone's looking. But the simulation hypothesis isn't without critics. Physicist Sabine Hossenfelder argues it's unfalsifiable, a clever thought experiment with no empirical hook. Others note the staggering energy requirements to simulate every quark in every atom. Unless the simulation is radically coarse-grained, approximating reality only at human scales, the computational load would defy even a Kardashev-type Roman III civilization. Then there's the recursion problem. If we're simulations, wouldn't our simulators also wonder if they're simulations ad infinitum? perhaps the most profound implication isn't whether the theory's true, but how it reshapes our existential questions. If reality is a simulation, does free will exist, or are we NPCs following predetermined scripts? Are the laws of physics just user settings, adjustable by some higher dimensional programmer? And if we one day create our own simulations, do we become gods or jailers? The simulation argument forces us to grapple with the nature of consciousness itself. If a simulated mind believes it's real, feels pain, experiences joy, is it any less valid than a biological one? While we may never crack this riddle, its value lies in the questions it sparks. Whether we're stardust or strings of code, the universe, real or rendered, remains a place of wonder. And if this is a simulation, let's hope the beings running it left cheat codes. The universe's greatest gift isn't just the answers it provides, it's the questions that keep us reaching further. Every cosmic riddle, from the phantom tug of dark matter to the whispers of potential alien signals, is a doorway to something deeper. Think of it like a hall of mirrors. Each time we solve one mystery, the reflection reveals another, more intricate puzzle waiting just beyond. Take dark energy, for example. We've known for decades that the universe's expansion is accelerating, but the moment we pinned that behavior to an enigmatic force, we realized we had no idea why it exists or what it truly is. This dance of discovery isn't just scientific progress, it's a testament to the cosmos's endless creativity. The same universe that hides 95% of its composition in the shadows also leaves breadcrumbs for us to follow. Consider fast radio bursts, those millisecond blips of energy from galaxies billions of light years away. At first, they seemed like cosmic static, random and meaningless. Then we found repeating patterns, subtle structures in the chaos, and suddenly, what looked like noise became a language we're just beginning to decipher. It's as if the universe enjoys leaving its most profound truths half-buried, waiting for us to dig a little deeper. And here's the beautiful irony: the more we learn, the smaller we realize we are. A century ago, we thought the Milky Way was the entire universe. Now we know it's just one of 2 trillion galaxies, each with its own stories, its own enigmas. Yet instead of feeling dwarfed by that scale, science embraces it. Every unanswered question is an invitation, not just to astronomers, but to anyone who's ever looked up at the night sky and wondered what else is out there. That's why these mysteries matter. They're not just gaps in our knowledge, they're catalysts for imagination. The possibility of life on Enceladus, the bizarre orbits of objects like Sedna, even the glitch-like inconsistencies in our quantum models, each one pushes the boundaries of what we consider possible. And with tools like the James Webb Space Telescope peering back to the dawn of time, and AI sifting through petabytes of cosmic data, we're standing on the brink of revelations we can't yet imagine. So here's to the unsolved, the unexplained, and the utterly bizarre. Whether you're a scientist, a stargazer, or just someone who loves a good mystery, remember, the universe isn't just hiding its secrets. It's revealing them, one tantalizing clue at a time. The only question left is, which riddle will we crack next? Drop your wildest cosmic theories in the comments below. Hit like if you're as obsessed with these mysteries as we are. And don't forget to subscribe for more deep dives into the universe's greatest unsolved puzzles. Until next time, keep